Before we go into the details of the graph plan system, I want to start with a simple example that we will use throughout this segment. This example is again from the DocWorker robot domain, so you should be familiar with that. And it illustrates the propositional representation, so it consists of a propositional planning domain and a propositional planning problem. To put the propositional representation in context, here's a quick reminder of classical representations, and I've shown you this slide before. So far, we have seen planning domains and planning problems represented in the strips representation. The strips representation is exactly like the propositional representation we will see next, but it uses first-order literals instead of propositions, so the atoms are relations that relate objects to each other. We have also seen a specific syntax that we can use to write strips representation domains and planning problems, and that was the PDDL language. Now, in the propositional representation, a world state is simply a set of proposition symbols. And as opposed to first-order literals, symbols don't have an internal structure. And then the actions in the propositional representation consists of precondition proposition, propositions to be added and to be removed. So the propositions to be added are the positive effects, and the propositions to be removed are the negative effects. The precondition propositions correspond to the positive preconditions in the strips representation. And this is another difference between the strips representation, as we've seen it so far, and the propositional representation. In the strips representation, we had positive and negative preconditions, and now we only have positive preconditions. As it turns out, this isn't much of a restriction, as every strips planning domain, every strips operator that has negative preconditions can be translated into an equivalent domain and operator that has no negative preconditions. So any problem that can be represented in one of these two representations can be translated into the other without much difficulty. And just as a reminder, there was also a third flavor of this type of representation, the state variable representation, but I won't go into detail here as we're not going to use it in this segment. But as a reminder, this representation is also essentially equivalent to the strips representation. So nothing can be said in one of these three representations that can't be said in the others. And here is an example world state from our simplified DocWorker robot problem that we will be using in this segment. In this state, we have only two locations, location 1 and location 2, and they are connected by a path, as you can see in this image. The two robots are called R and Q, or robot R and robot Q, and are at the two locations initially, R at location 1 and Q at location 2. Both robots are currently unloaded, but there are also two containers in this state, and the two containers are container A and container B at the two locations as shown here. What's new here is that robots can load and unload the containers autonomously. So each robot has its own personal crane attached to the robot that it carries around with it. Also, we will now think of locations as being big enough for multiple robots. Otherwise, there wouldn't be much we could do in this state because both locations are already occupied. That really simplifies the problem a lot. And the problem is then given by a set of actions, which I will describe shortly, an initial state, which is shown here, and a goal description, which simply consists of a state in which the two containers are swapped. So in our goal state, we want container A at location 2 and container B at location 1. And here are the operators in the strips notation as we can use them for state transitions in this simplified domain. The first operator we have defined here is the move operator, which moves robot R from location L to location L prime. And since there can be multiple robots at the same location, the preconditions and the effects of the move action are actually a lot simpler than what we've seen previously. Similarly, we have simpler load and unload operations that take fewer parameters and have fewer preconditions and effects because the crane is now attached to the robot. That also means we don't need a take and a put action for the cranes. One nice side effect of this simplified problem is that none of the operators have negative preconditions. As I've just mentioned, that is one of the features we need for the propositional representation. Another interesting observation is to do with the number of possible actions that are instances of each operator. So looking at the move action first, we have two possible robots and we have two possible locations that we can use for L and two possible locations that we can use for L prime. So in theory, that means there should be 8 possible instances of this move operator. But when we look at the preconditions of this operator, we have one precondition in here that is static. That is, this relation never changes from any world state to another. So when we translate our operators into actions, we can exploit that. We now know that for this operator, there are two possible robots. And for this pair, L prime, there are two ways we can satisfy the adjacent relation as defined in our problem. That means we have to multiply this by 2, giving us 4 actions that are possible in this problem. Now, let's have a look at the proposition symbols we will use in our example to represent world states and actions. And since we'll have to handle quite a few of these symbols in our examples, they're actually very concise. For example, we have the symbol R1 that we use to denote that the robot with the name R is at the location 1, R1, and R2, meaning that the robot with the name R is at location 2. The strips representation for these two symbols would have looked something like this. R1 is at robot R location 1, and R2 is at robot R location 2. Similarly, we have equivalent symbols for the other robot, for robot Q. This symbol means that robot Q is at location 1, and this symbol means that robot Q is at location 2. And we also need symbols to express that the robot is not loaded with a container, and we use the symbol UR, meaning that robot R is unloaded, and UQ to indicate that robot Q is unloaded. So that means we have 6 symbols to talk about the two robots. But we need more symbols to talk about the containers. And here we have the symbol A1, for example, meaning that container A is at location 1. Or more specifically, it means that this container is at the unique pile that is at that location. So it is not on a robot that is at location 1, but really in that pile at location 1. Similarly, we have a symbol representing that container A is at location 2, in a pile at location 2. Or we have a symbol that says that container A is on robot R, or the final location for the container, it can be on robot Q. This is container A loaded onto the robot Q. And we also need equivalent symbols for our second container, container B, and we have those here. B1 means container B is in the pile at location 1. B2, container B is in the pile at location 2. BR, container B is loaded onto robot R. And finally, BQ, container B is loaded onto robot Q. So that means we have altogether 8 more symbols to describe the state of the two containers. And of course, these symbols are already sufficient to describe our initial state, which is given here. In our initial state, our robot R is at location 1, whereas robot Q is at the other location, location 2. The container A is in the pile at location 1, and container B is in the other pile at location 2. And both robots are unloaded. These are all the propositions that are true in the initial state, and all the propositions not mentioned here are false. And here are all the symbols we will use to represent actions in this domain. Let's start with the available move actions. And again, the symbols I'm using for actions are quite concise. So this symbol here, MR12, represents the action of moving robot R from location 1 to location 2. The first thing you note here is that the first letter representing the action is a capital letter. I have used symbols with lowercase letters for state propositions, and I will use symbols starting with an uppercase letter for action propositions. And the first letter indicates which action this is. M for move. Then there are the parameters represented by single letters here, namely R, we're moving robot R, and we're moving it from location 1 to location 2. Then similarly we have MR21, indicating that we're moving robot R from location 2 to location 1, representing this action, this instance of an operator. Similar actions for robot Q are MQ12, meaning we're moving robot Q from location 1 to location 2. And here we have MQ21, moving robot Q in the other direction from location 2 to location 1. So these are the 4 possible move actions that exist in this problem instance. Similarly, we have actions representing loading of containers, and these all start with the capital letter L, like LAR1, meaning we're loading container A onto robot R at location 1. And here is what that was as an operator. Then we have LAR2, meaning we're loading container A onto robot R at location 2, and so on. We have symbols for loading container A onto the different robots at the different locations, and symbols for loading container B onto the different robots at the different locations. And finally, we have the unload actions. The unload actions start with the capital letter U, like UAR1 here, which means we're unloading container A from robot R at location 1. And of course, the other unload actions follow all the same pattern. We have the letter U followed by the container we're unloading, the robot from which we're unloading it, and the number indicates which location this is happening at. So what we have here is 4 plus 8 plus 8, altogether 20 different action symbols representing 20 different types of actions, and we had 14 different proposition symbols that we use in states. So altogether we have 34 different symbols we need to deal with. And that concludes my simplified DWR problem in the propositional representation.